Welcome to Air Quality Matters, and this is a conversation with Ben Jones. Ben is an associate professor at the University of Nottingham in the Department of Architecture and the Built Environment. With a master's degree in aeronautical engineering, he worked as a senior software engineer at BAE Systems before completing an engineering doctorate in environmental technologies at Brunel. He was a research associate at University College London for 2 years before taking a post in Nottingham in 2013. The focus of Ben's work is on the measurement and modelling approaches of the indoor environment. He is particularly interested in energy efficient ventilation of buildings and its relationship with indoor air quality and occupant health. Ben's work has provided strategic policy analysis to UK government departments, international organisations and businesses. He is the UK's representative on the board of the Air Infiltration and Ventilation Centre, the AIVC, an annex of the International Energy Agency, and a committee member of the Chartered Institute of Building Services Engineers Natural Ventilation Group. Every now and then, a piece of work comes along that has the attention of the room. And the work that Ben and his colleagues have been responsible for on harm is right up there. It's about the harm that pollutants may actually cause and ways we can better define it and ultimately what we consider to be good and bad air quality. It's genuinely fascinating, raises questions undoubtedly, it certainly answers questions, annoys a few people, which is always fun, but most of all, it just makes a lot of sense. We talked about much more, of course, including relative risk, cooking pollutants, and what he's working on right now. As always with Ben, it was a genuinely fascinating conversation. I hope you enjoy it. Thanks for listening. This is Ben Jones. So, Ben, what I want to ask you was, we hear this term the whole time, indoor air quality. It's used everywhere. But what does that actually mean? I'd love to get your definition of that and what that perhaps leads on to when we start understanding what good or bad of that means.
Yeah, that's a good question to start with, isn't it? I think if you talk to different people, you get a completely different answer. But if you break down the three words, indoor air and quality, we probably agree on two of them and disagree on one of them. So if we take indoor, then it relates to the environment in a building, but we're probably interested in what goes on around the building as well, particularly if it's air, because it's probably going to come inside if you're ventilating and there's infiltration too. And then the air bit, well, then there's the invisible gaseous substances, nitrogen, oxygen, argon, and so on. We're not too interested in them. We're interested in the bits that you wouldn't normally find in air, so which we would define as a contaminant. A contaminant then becomes a pollutant if it's known to cause health at the concentrations you find it. But we'll call them contaminants here on. So we probably agree on that too. It's then when you come to quality that we might disagree. Now, if you look at a dictionary definition, it's a measure of excellence. So it's a relative parameter. I guess a horse was considered to be an excellent mode of transport until the car was invented. And if you got on a horse now, you probably wouldn't think that, gosh, this is excellent. So when we think of indoor air quality, it's relative to something, but what are we considering it to be relative to? Is it the quality of indoor air relative to it being uncontaminated? This may not be an efficient approach, as we'll delve into later, because we may be expending resources on designing, manufacturing, running systems that are completely unnecessary. So how should we think about it? Should we strive for the best? Should it be the most excellent quality, or should it just be good enough? Should it just be acceptable? And what would make indoor air quality acceptable? So it then depends how you think of quality as a category. Now, I really like the ASHRAE definition, which I can give you if you like.
Can you remember it
Oh,
verbatim?
yeah, I can go verbatim. So ASHRAE 62.2, which is its standard for ventilation and acceptable indoor air quality in non-domestic buildings, says that it's air in which there are no known contaminants at harmful concentrations determined by relevant authorities, of which a substantial majority of people exposed do not express dissatisfaction. So this acceptability is binary. It's often confused as being a categorical variable in that it might be bad, poor, acceptable, good, excellent. It's not. It either is acceptable or it isn't acceptable. So you could have a building that is acceptable today, but if you change the parameters of acceptability, it may not be acceptable tomorrow. And the really neat thing about the definition is it automatically builds into it um, change. So as more information becomes available, we can redefine what acceptability is. So at the moment, we have our current information, and that's where we're at.
That's interesting because the language suggests acceptable as some kind of compromise in some way, that we're accepting a certain level, which I suppose in one way you are. You're saying it's an acceptable level, but it is a line that you've crossed, that it is now acceptable or it isn't. And that the beauty of that definition, as you say, is it could change over time as we learn more, or even our pollutants around us change. Like, for
Right.
example, formaldehyde was much more of a problem 20 years ago, 10 years ago, than it potentially could be in 10 years' time as we
Mm-hmm.
reduce the level of formaldehyde in products. So having a definition that doesn't say this particular number is acceptable is handy, isn't it? Because we can move those goalposts, those threshold goalposts, if we need to.
Yes. What we want is to remove subjectivity wherever possible so that whatever is used to define acceptability is objective. So we want to use the science, to use an overused phrase from the pandemic. Trust the science and follow the science rather than having people make political decisions in order to appease people or organizations or whoever, polluters, let's term them that.
So going back to that ASHRAE definition, um, where there are no known contaminants at a harmful level, as defined by cognizant or authorities that should know what they're talking about. Currently, that's done typically through thresholds, right?
Yeah. So uh, the metric that's used at the moment is known as a threshold limit value, um, and they're generally a maximum average annual airborne concentration of a contaminant to which a healthy person should not be exposed to over the course of a year. So it's normally done over two periods actually. So I've just said a year. Um, the harm that people will experience can be split in two ways. So it can occur over a short time frame. Conventionally, that's called an acute time frame, and it's normally less than 24 hours. So you see the response pretty quick, and then you can do something about it because you could say, "Oh, my throat hurts, or my nose is sore, or my eyes are watering," and you open a window, say, or you leave. Um, Chronic effects occur over timeframes greater than 24 hours, and it's normally way longer than that. We're talking decades. At which point you've got some disease which you takes a great deal more time and effort to treat. So you normally have two threshold limit values. Your higher one for acute timeframes, and then a lower one for chronic timeframes. Problem with the threshold limit value is it's not really clear. So if you exceeded or are under it by say 10%, what does that do? Is that good? Is it really good? Does it reduce your risk by 10%? Say, um, that's a bit of a problem.
So that's where you're starting to try and then under, understand or create a link between uh, a level of exposure to a pollutant and the potential harm that it could cause, because
Right.
those two are linked. I mean, we're not interested in a level of pollutant if it doesn't cause us very much harm, or we're not exposed to it for a long enough period of time for it to cause us harm. So I think in air quality parlance, that might be quite a nice thing to explain for people, is that we consider how much harm something can do us on a number of factors, don't we? Including time, amount, how vulnerable we might be to it. There's a whole number of things that we actually care about when it comes to a pollutant, isn't there?
Yes. So just being in the same place at the same time as a contaminant means you're exposed to it. The dose that you will actually receive then depends on a whole bunch of other factors. So it affects your metabolic rate, it's the volume of your lungs, um, it, and so on. So it becomes quite clear then that what you're doing in the space and who you are or who is in the space matters. The thing is, when you consider these at a population level, these things sort of average out. So the specifics probably aren't so important. It's just that different organizational bodies treat these differently. So if you look at, you mentioned formaldehyde, but if you take particulate matter, a whole bunch of different organizations will give completely different thresholds for the same contaminant, which is a bit of an issue, isn't it? And what we want to know really is um, that they should all be the same. Really, they should all be based on the same amount of acceptable harm. And if we acknowledge that there's no such thing as zero risk, um, but
Yeah,
some
interesting.
risks can be acceptable.
Yeah, it's that link between the human impact and the fact that it just exists.
Yes.
Is some of that due to, do you think, to the tradition that these air quality thresholds have typically been about outdoor air quality limits, or has that got nothing to do with it? Is it just it's just traditionally we've always set a threshold value for a particular pollutant based on whatever evidence there was at the time that we wanted to keep it below a certain value, and that's it? Or is there something
Yeah.
about the fact that a lot of the pollutants that we think about have typically been outdoor air quality pollutants, and we think in a different way? Is there anything to that?
Mm. Well, I think you have to remember that nitrogen dioxide or formaldehyde outdoors is exactly the same as nitrogen dioxide or formaldehyde indoors. For particulate matter, that may not be necessarily true, but there are ways around thinking about that mean that we don't have to worry about it too much right now. Um, I guess what we've done is we've taken outdoor thresholds. One, because we've traditionally been interested in outdoor air an awful lot longer than we have indoor air. So we've just taken those metrics and brought them and applied them indoors. I can't think of any other reason why they would be too different.
And ultimately, the vast majority of our exposure to outdoor air is indoors anyway, because we
Right.
spend so much time indoors, don't we?
Yeah.
Yeah.
So the current figure is what, 90% indoors, 70% in our own homes. So then
Yeah.
what, 30 odd percent time in our own bedrooms. So if you want to know where to start looking to reduce risk of exposure to airborne contaminants, it's indoors where you start, and then in your own home, actually.
So that's a fabulous segue, as if intended, Ben, um, into I wonder how we could start looking at harm in our homes and start to create some metrics to understand how much harm this stuff does us. And hey presto, you and your colleagues have been working um, on looking at the harm of indoor air quality, particularly in the residential setting. Um, Originally inspired from what I heard from you from work that was originally done by Max Sherman, Logan Price et al., basically.
Yeah,
Is that right?
that's true. Um, you interviewed Max a couple of weeks ago, and the podcast was brilliant because he gave so much context and really set the platform for our discussion today, which has been very helpful. But I've known him, I think, since about 2012, and I walked into a lecture theatre where he was giving a talk, and he showed us this plot. Now, as an academic, as a professional nerd, I'm allowed to have a favourite plot, and it is my favourite plot. On the x-axis, you've got a whole bunch of contaminants, and on the y-axis, you've got a metric that I had heard about but not seen used before. I was just starting to use it in our own work at University College when I was there in a different form. But it's a metric that allows you to quantify harm. And what it showed was is that there were really three or four contaminants that caused a huge amount of harm, and the rest didn't. And there was some clear take homes from that is that it told you where to start looking. So if the stats already tell us to look at, we need to start thinking about buildings for our exposure to airborne contaminants. And if they then tell us we need to start looking at homes, it then told us which contaminants we needed to start looking at in homes. And then Max and I talked about this for about 5 or 6 years until eventually we managed to get some money to look at it and reevaluate that work because it was an initial cursory look. And I know that my academic colleagues were really interested in it, they didn't really know what to do with it. And so we'd all sort of put it in papers and referencing papers and technical manuals and so on, but we'd never done anything to try and get it into regulation. So what we did was we went back to the drawing board, and we went back to Jenny Lode's work. They looked at 77 studies reporting on air contaminants in the US. So it was US specific, but they also took some contaminant concentrations for contaminants, these 77 contaminants from other countries with similar lifestyles, like the UK. So they started off with 267 chemical air contaminants in total. And they looked at the annual health impact of those compared to a no exposure case. So they compared the harm relative to not being exposed to these at all. And in the end, they whittled it down to just a few contaminants. So if contaminants didn't appear on the list, it was either because there wasn't data for them or the harm just was so low that it wasn't worth putting them on the plot. So I think they got down to just over 40 contaminants. So the take homes then were that particulate matter, secondhand smoke, radon, formaldehyde, and acrolein, as the Americans call it, acrolein as we call it, mattered quite a lot. Maybe ozone and too. Our reanalysis of that changed things a little bit. We didn't look at secondhand smoke because it's very easy to get people to smoke outside. That's not really something we should be ventilating to change. That's a source control issue. So we started with their contaminants, and then we added some conversations with the US EPA or somebody from the US Environmental Protection Authority, and we added a couple more. But once we come to the bottom of it, things didn't change too much. What we were able to do is reduce uncertainty in the predictions, but it essentially meant that we now had just a series of contaminants that we could deal with. Now, there are a couple of interesting things that arose before we got to the harm that I can go through. So in order to get the harm, we needed concentrations. So we looked at just over 800 different data sets of contaminants in homes, and the contaminant that is most abundant in homes is ethanol. By mass, you get plenty of ethanol in homes.
Explain to people maybe where ethanol is coming from in the home.
Well, it's a good preservative, particularly in wood. Same with formaldehyde. It also comes from wood products too. In fact, formaldehyde is a great store of formaldehyde in homes is MDF. But the other contaminants that were particularly abundant were PM10. So that's particulate matter with a aerodynamic diameter of 10 microns or less. PM2.5, so that's got an aerodynamic diameter of 2.5 or less. Nitrogen dioxide, formaldehyde, and ethanol.
And was that's very similar also to the most reported pollutants in studies as well. So there's been a lot of studies on PM2.5 and formaldehyde and NO2. I mean, also on toluenes and benzenes, for example. But is it just the way it is that it just so they happen to be the most abundant, or is it the fact that they're the most studied that you see them the most? Is there a correlation between what people are looking at and what we find, or is it a coincidence?
I think it's called is it called the street lamp effect? You know, where the person's looking for something under a street lamp, and the person says, "What are you doing?" And he says, "Oh, I'm looking for my car keys." He says, "Well, where did you drop them?" "Over there." "Well, why aren't you looking over there?" "Well, the light's over here, so I'm looking here." And that could be a slight problem here, in that we can only work with the data we've got. But as
Yeah.
my colleague Ian Walker at Lawrence Berkeley points out, so much of the harm does correlate to particulate matter of various diameters. If there's some contaminant out there that we haven't found yet, it's almost certainly going to be correlated with PM2.5. And in which case, if we treat the sources of PM2.5, we're probably likely to treat the source of some mystery contaminant too. But we do have a lot of data. You know, it's 136 studies, 827 data sets. The contaminant concentrations represent the global north, so they're predominantly from the US, Canada, China, the UK. We're talking about fairly houses constructed of bricks and mortar and wood and so on in the last few hundred years generally.
I was going
So
to ask
we're
you
not,
that. So they are
yeah,
reflective of the kind of homes that we live in, predominantly in
well,
North America and
sure.
Europe and so on. Yeah.
Yes, but they will account for people doing what they do in their homes. So they will cook. They will have open fires. With the energy problems we've got at the moment, people are using a lot of stoves and open fires. They'll smoke. They'll burn incense. They'll vacuum. They'll release air fresheners and cleaning products and so on. All the things we know that are common contaminant sources in home. They'll all be accounted for in there, which is what we want, because we want that all to average up over a very large data set. So we have a good understanding of what's going on. Because of course, one of the things that we can do to treat is to consider behaviour, not just to ventilate. There's that wonderful phrase in there from Petticofer, who says, if you have a pile of manure in a room, remove the pile of manure, don't ventilate.
Source control. And
Indeed.
so this work led you to say, right, okay, in the first instance, if we look at the type of homes that we're interested in looking at, what are we
Yes.
finding in those homes? And as you say, the most abundant are ones that we know cause harm,
Mm-hmm.
like PM2.5 and formaldehyde, but also a lot of other pollutants like ethanol that may not be so harmful. So I keep using this word harm. How do you start to define what harm is at a very basic level? Because we've already heard you mention things like DALIs. So maybe
Yeah.
speak to that a little bit about traditionally at a population level, how we start to view the harm of certain risks and the kind of data that you were looking at to arrive at that, the epidemiological and the toxicological data, and what that really means in plain English when you're starting to root through that kind of data. How do we turn an epidemiological study into a DALI, for example?
Okay. So if we begin with the end in mind, which is the DALI. So the DALI is a health adjusted life year metric, and there are a number of these. QALY is another one, which is used here in the UK by the National Health Service, and the disability adjusted life year, as opposed to the quality adjusted life year, is used by by the World Health Organization.
What's
And
the
the
difference
reason we
between the two, Ben?
well, so the QALY considers the years of life lived in full health plus the life years lived with disability, whereas um, the DALI is not interested in the life years lived in full health. It is interested in the life years lived with disability, but it's then interested in the life years lost due to premature death. So they both cover the bit with disability, but QALYs are interested in the bit before, and DALIs are interested in what happens after. We went with DALIs because there's just more information. Um, I suppose if we were trying to influence the British government here, which was not an aim necessarily specifically, we might have tried to use QALYs, and that's something perhaps we can look at in the future. But we went with disability adjusted life years. So the disability adjusted life year then has two parts to it. It counts the years lived with disability. It counts the years of life lost, and it gives you a whole number and population scale. It enables you then to quantify those disability adjusted life years from common hazards. So alcoholism, for example, is 1,200 DALIs per 10 to the 5 people per year. Smoking, 2,600, and transport injuries about 1,000. So that's the
Okay, so
metric that we wanted.
so just again in plain English, 10 to the 5 is
It's 10,000,
100,000,
100,000, sorry, 10 to the
100,000.
6 is a
Okay.
million. Yeah, it's 100,000 people. And the
So
reason it's split to there is because it gives us nice numbers that we can deal with. An interesting example is, by the way, is the World Health Organization has an aspiration for DALIs for drinking water, which is 1 in 1 million, 1 DALI per million people per year. We don't get close to achieving that for drinking water, I'll point out, but that's the aspiration.
interesting. So
It doesn't use
effectively,
DALIs for air.
so a DALI is giving you a number, ultimately a metric for
Yeah.
the years lost to full life and disability per 100,000 of the population. So you cited alcohol there, or alcoholism, I guess,
Mm-hmm.
1,200 people per 100,000, or years lost to
It's
disability and life per
years of life.
100,000. Yeah.
Mm-hmm.
Okay. So it's a useful metric because it creates a level of harm at a population level that, I guess, going back to the original idea behind DALIs, is you can convert that to a cost to society, either
Yes.
monetary or societal costs.
Yeah.
That
But it
gives
comes
us
back
that
to the
answer.
it comes back to acceptability too,
Okay.
because some of these clearly are acceptable at a population scale. There is no great clamour to reduce transport injuries, as far as I can tell, hugely. It's not certainly not a frontline political issue. I'm sure there are groups who want to do that, and for good reasons. But transport injuries are 1,000. Um, that may be, to most people, an acceptable risk and an acceptable number of years of life lost to disability and premature death, given the
Well,
benefits that we get from transport.
I guess it comes back to those cold, hard decisions that have to be made at a policy level of how much will it cost for us to reduce an impact
Yeah,
for 500 DALIs per 100,000 people. Is it worth it over and above the costs we might have to spend to reduce it by 1,000 in another pot somewhere else? At
yeah,
some point, somebody's got to make a decision to make a change at a policy level, at a political level, to do something, and it always comes down to what will the impact be and how much will it cost us to achieve that impact. But at the very least, with these kind of formulas, it gives us a number, which we've always really struggled with air quality, haven't we, to
yes,
create this link between ventilation, air quality outcomes, and health outcomes.
yes.
Joining those dots has always been quite difficult.
The comforting thing is we don't have to make the decision, by the way. We just produce the numbers and then hand that over to the politicians and the policymakers. So it's not up to me, for example, to say that 1,000 DALIs is acceptable for transport or air quality.
Okay, so you're looking at some 800 data sets
Mhm.
of, from what I understand, a mix of epidemiological studies, toxicological studies, and a mixture of both, and trying to figure out how much harm these cause. Have I got that right, or was it's 800 data sets that you then had to look at the epidemiological evidence and toxicological evidence for, and
Yeah,
translate that into some impact? Maybe explain that, and perhaps even for people as dumb as me, the difference between epidemiological and toxicological studies, Ben.
and you're definitely not dumb, Simon. Let's lay that one straight. Um, the 827 studies was for concentrations, but in order to turn those concentrations into some harm, we needed to have a model that related the DALI to a concentration. And there's two sources of information we can use for that. The first comes from epidemiological approaches, which are population studies of health impacts, which are statistically related to exposure to different airborne contaminants. Um, they are often differentiated in by by individual health impacts, but because we're ultimately interested in regulation at the end, we add them all together. You can do that. It is possible to do that. And perhaps we can talk about problems with that, synergistic effects, and so on later on. But so there's this population data that we get. The second is toxicological data. So we don't actually measure that many contaminants in outdoor air. So we're reliant then on getting information about the relationship between exposure and response um, in other ways. So often they come from animal models, and they're done over shorter time frames, and then they're extrapolated to humans over a long time frame. However, for the contaminants where we had information from both epidemiological and toxicological sources, there was reassuring agreement. And the relationship then between the response, the health impact, and the dose. So the concentration is no, we're not interested in dose, sorry, it's an exposure, I suppose. Um, but conventionally, that relationship is nonlinear. So it rises up and then plateaus off up to a threshold. But the part of that relationship that we're operating at with concentrations indoors is approximately linear. The
Oh,
concentrations are low enough so that the relationship between the harm and the exposure is linear. And that means you can have a simple product equation, A equals B times C, where harm, in our sense, then was some amalgamation of all the information that comes from epidemiological and toxicological studies times the annual concentration equals the harm. Now, this new metric then was what we call a harm intensity. So this has units of disability adjusted life years per microgram per meter cubed in exposed to per 10 to the 5 people per year. So it's essentially the harm per unit mass of exposure that you're for the contaminant. So we can then start to look at which contaminants, if you were to receive the same concentration from all of them, matter the most. And here it comes down to particulate matter again. So PM2.5, PM10, chromium 7 is a new one we haven't mentioned yet, nitrogen dioxide, and then formaldehyde. Now there is a problem here, and that's that the particulate matter diameters are a less than number. So PM10 is 10 micrometers and less. PM2.5 is 2.5 microns and less. So contained within the PM10 information is PM2.5 information. So we had to separate them out. So we created a coarse fraction harm intensity. So that's between 10 and 2.5 microns. And that is important too. So that still makes it into our top 6. But if you were looking at population harm, then you would exclude the PM10 because otherwise you're double counting. So particulate matter generally matters, as we're going to see in a moment when we come to the two. So if we move on to that, so then the product of the concentrations we looked at and then the harm intensities then give us the total harm.
Okay, so
And
let's just
all right,
reverse gear a little bit and re-summarize for people, because there's a lot of stuff there in quick succession. But if I was to try and summarize it as simply as I can, we looked at the evidence we had for what pollutants we found in our
yeah,
types of homes,
mm-hmm.
how much of them there was, what we're most interested in, because there's no point having a look at something you never find particularly. But there was a certain, there's some we find all the time. Then you looked at the harm these pollutants caused. So all things being all equal, with the same exposure to all of them, you looked at which were the most harmful.
Yes.
Uh, so now when you have that value, you can now look at the ones you are going to be exposed to with this harm intensity and look at the total harm they're likely to cause. So take a very simple example, the ethanol one.
Mm.
There's a lot of it, but because it's not as harmful, say, as formaldehyde, its total harm that it would cause you with this new metric is very low. We don't really see it factoring in the top 5, 10, or 15 even. Whereas something like formaldehyde, where you may not be exposed to as much of it as ethanol because it's more harmful, its total harm is higher. Is that a
Yes.
reasonable summary of what you've
Yes.
just said? Yeah. So we're basically saying what causes us harm, how much of it you're exposed to. Now we know the total harm. We've now got a value that can tell us what we need to be interested in the homes, because there's no point worrying about something we never see, or there's no point worrying about something that doesn't cause us much harm if
Right.
a certain bunch of them, which I guess you're going to come on to in a minute, cause the overwhelming amount of harm that we would experience. Is that fair to say?
Yes. Very fair to say indeed. Yes. If it's not there and it's not harmful, then we don't need to know about it. And even when it is harmful, if it's not there, we don't need to know about it.
And hasn't that been a problem typically in the past, is that in the indoor air quality community, we tend to get our knickers in a twist over VOCs because there's just so many of them, and they could all potentially do us harm by various degrees, and they all interact with each other and change and increase and decrease with humidity. It's unbelievably complicated. So we spend an inordinate amount of time running around in circles, worrying about all of these different chemicals we see in our built environment. But if they just don't cause that much total harm, we could probably be worrying about some other things instead, couldn't
Yes.
we?
I
Yeah.
think some standards or guidelines at least are very guilty of giving us lists and contaminants, and I'm not sure what the average engineer thinks they're supposed to do with those. After all, they probably don't possess the equipment to even check, and they're trying to measure stuff is really hard. We can come on to this later, perhaps, because that's interesting to talk about diagnostics. But I think if you're going to be trying to produce regulation, you just want to focus, at least initially, on those that really matter, those that are going to harm our population the most. Um, and bear in mind, we're talking about chronic harm here. We're not talking about the acute bit. We're talking about the thing that's going to cause our health services problems in decades to come.
And the
So yep.
and the reality is, in the residential built environment, there's only so much you can do with acute exposure, and that's typically dealt with purge ventilation and source control. We often talk about acute exposure in workplace local exhaust ventilation type conversations. But really, we're interested in the home, in chronic harm, because it's where we're exposed to certain pollutants for the majority of our lifetime. So with a roll of the drum then, Ben, uh, what what did the study find? What was the outcomes of the total harm when you took all of these things into consideration?
So yeah, we've taken a long time to get there, haven't we?
And we
It's
just, yeah.
it's it's particulate matter that matters the most. PMs matter. So air quality matters, but of the contaminants in homes that exist, particulate matter matters the most. PM 2.5 is the most harmful by around an order of magnitude. The coarse fraction matters too. Nitrogen dioxide, formaldehyde, radon, and ozone. And thereafter, the harms drop off so much that it's multiple folds of reduction before we are interested in them, really. And that makes regulation quite straightforward now. So even radon, for example, we don't have to put in necessarily because it's more a source control issue. There are many great remedial measures that can be undertaken to reduce the transmission into a space. Although maybe uh, with your experience in Ireland and talking to James McGrath and so on, who's a colleague at working on radon in Irish homes, he would say not all of those work. So maybe it is needed. But either way, that still brings it down to what is it, two, four, six contaminants really, and you probably get away with just five because most of the sources of particulate matter for PM 2.5 and the coarse fraction are the same. So just by regulating one, you're going to get the other one too.
So let's discuss those results a little bit. So
Okay.
the first one and the standout out of these results, and not a surprise to a lot of people that look at the harm of indoor air quality, is particulate matter is right up there and significantly more harmful than many of the other pollutants that we traditionally talk about. And this is principally because, without straying too far outside of our skill set, we can breathe them in, they get deep into our lungs and can be absorbed into our bloodstream, for example. That's my broad understanding of particulates. I suppose from an
Yes.
engineering perspective, it's good news from the built environment's perspective because we know how to handle particulates, don't we? It's a pollutant that we're well used to managing.
Yes. Well, we can get straight to your hierarchies of control, which I know you're very fond of, and so it means wherever possible we can remove the source. One of the primary sources is cooking, so I don't think we're going to persuade people to cook outside. But it then means that you need targeted interventions. So it means then that things like cooker hoods become incredibly important, and maybe behavioural controls too. When people are cooking, cleaning, so on, they should crack open their windows. They should turn on their cooker hoods, even if they're cleaning, because this thing will act like a fan anyway. And in order to try and reduce exposure to them.
Yeah, indeed. And then, like, so particulates we can handle by good background ventilation, exhausting it at source wherever possible, good behavior and framing and communication around the importance of managing particulates, because these aren't things we can see. We don't know that they're there necessarily. We can predict they're there by our activities, but it's not, we can't see 2.5 in the air. It's not like a smog in the home necessarily, is it? We do have to understand that we have to deal with it like some of the other pollutants, that we're not going to pick up that it's present.
Right, and there's 10 to 12 micrograms per cubic meter in the outdoor air permanently. So, or recently we've just had uh, bonfire night, Guy Fawkes night, where we have lots of bonfires and fireworks, and it really does rise up then. So
Yeah.
seasonally we have some really bad air quality issues here in the UK, and there's not a lot we can do with that. Um, this is where we have to start thinking about new ventilation systems that pre-filter air as they come into our homes. Maybe we have to think about the effect of filtering systems within the home, so air purifying systems that then filter out particulate matter. This is a frontier really, and something that I think if you were going to consider in 10 years' time, or in fact, it's probably going to have to be much sooner than that. In fact, so this is something that we need to start thinking about right away.
And this is why the work on harm is so important, because it joins the dots for us in that sense. If we can say, look, this is as harmful as X, it makes it tangible for people.
Yeah,
I mean, some of the things in there are definitely source control problems, right? So formaldehyde typically is a source control problem to solve, and we've seen that reducing over time as we see lower formaldehyde products. Um, Radon, as you say, typically it's kind of a source control, but really an engineering problem as well. Like your home
mm,
will either be in a radon area or it won't, and if it is, then there are certain things you can do from an engineering perspective to separate yourself from that harm with radon barriers and sumps and good background ventilation, for example. The ones towards the lower end of that list may be a little bit more confusing for some people. So we see NO2, so nitrogen dioxide, appearing towards the bottom of that top five, shall we say. That's coming from combustion in the home, typically, is it? Or is that being pulled in from outside from traffic pollution sources, for example?
or both.
Okay.
So, so if you've got so if you've got traffic nearby, as any burning, any combustion engines nearby, then it would be produced by that. It's produced in the home from particularly if you've got gas hobs or a gas fire, then then you'll get nitrogen dioxide emissions then. And the way around that, I suppose, is to eventually think about switching your gas hobs for induction. Induction being the optimal because it's cooler than using electric coils, and using electric coils may introduce a whole bunch of other things if they're not cleaned properly, particularly particulate matter is what I'm thinking of. But in the short term, it comes back to your cooker hood, and the cooker hood captures anything that, if it's designed well and installed well and extracts to outside, then it will capture a significant proportion of whatever is emitted under it. The problem is at the moment is people either don't use them or they don't work very well, and they're not regulated at the moment. So this is an area for change too.
Yeah, I completely agree. The one of the ones on the bottom of the list, which I confess I don't really understand a lot about, is ozone, both in the sources of it in a home, and why it causes harm. Why do we see ozone there above? I know you said before my favorite pollutant isn't on the list. How comes? Not a lot of people would have picked ozone, I don't think, as one of the ones on the list. Why is it there, and where do we see it coming from? Do you know?
So most people expect ozone to appear in the upper atmosphere. It was something that was talked about when we had a hole in the in the in the upper atmosphere, and was leading to lots of overexposure and sunburn and skin cancer. But it's a photocatalytic contaminant, so it will vary seasonally, um, and will be brought in from outside quite a lot. The reason why it's particularly of interest is because it is so reactive. And when it reacts with other things in the air, it tends to produce things that aren't very nice. And one of those things that it produces is formaldehyde, which is on the list.
Okay, interesting. So it's as much about the company it keeps, ozone, as it is about the pollutant itself. It creates other pollutants as well. It's an
Yes, this
interesting
is where
thing
we
in that
get
sense.
get into the realms of airborne chemistry, and why it's not just an engineer. I mean, the solutions are engineering problems, and why we desperately and definitely need our chemistry colleagues to work out the minutiae of what's going on, so that we can make sure that we're capturing the right contaminants and looking for the right things, and removing the right things.
Yeah, interesting. And so one complaint from me as someone that spends their life talking about condensation, damp, and mold, is my favorite pollutant isn't on the list, Ben.
What's
Um,
that?
I suppose bioaerosols. So it's a question you get asked a lot: is that why is my favorite not on there? Because it's the thing I've been looking at for the last 5 years. Ultimately,
Yes.
this is down to the available evidence you have from a study's perspective, running it through a formula, and the results you get are the results you get. If new evidence comes to life, I guess going back to that ASHRAE statement at the beginning, then those outcomes may change. But what appears to me is that even if there's some fairly significant changes in those pollutants lower down the list, they're going to have to change a lot, aren't they, to have an impact on something like particulate matter?
Absolutely. Um, One of the most contentious omissions, if you like, is for the contaminants of concern. So the contaminants of concern are the six contaminants that lead to over 99% of the harm at population scale. It's one of the most contentious emissions is benzene, which often appears on lists of contaminants that should be regulated in spaces. And it's contentious because it's a class one carcinogen. But the 45 contaminants we considered, 35 of them are carcinogens also. So the reason these contaminants don't appear on the list is either because there isn't enough information, or because what it tells us at the moment is that it doesn't matter relative to others at the moment. And until the information changes, there may be some lifestyle change, there may be some new technology, some new material which introduces these in the future. But the way things stand at the moment, those are the top six that matter the most.
So to steel man that position just for a moment, there's the issue of them just not actually being that harmful, but there's also the challenge perhaps that there isn't evidence yet or enough studies around it. Is that lack of information a problem to a model like that? Can you make an argument that when models are only as good as the evidence that's available, that you may miss something? Um, I guess as a scientist, you can only work off of evidence. Would that be
Yes,
right? Like,
this is true. So I can only work with what is in front of me, but clearly we should really only be making decisions based around evidence. Otherwise, we're just including our favorite contaminant in there, and that's not an objective approach, that's a subjective approach. So clearly we should continue looking, and we should reflect and reevaluate at frequent intervals. And I would argue that the 10-year interval between Jenny Loeb's work and our Nottingham work is too long. This needs to be an ongoing thing. Um, but I think another way of looking at it is how much more of this stuff would there have to be, whatever contaminant that you're interested in, for it to start to break into the top six, if you like. And for some contaminants, that either the harm or the concentration, we're going to have been wrong by orders of magnitude.
yes, indeed. And I know I've asked this question of you before, and it's a question I did in a way pose to Max was, whenever you see a result like we've seen from you, where such an overwhelming amount of the harm comes from one pollutant, the immediate question is we getting something wrong? Why is this thing so stand out above everything else? And one of the questions with particulates is we tend to talk about it as if it's one thing, um,
Mm.
whereas particulate matter is a collection of things, both those that are maybe not so harmful and some that are very harmful. Is there a risk when you have something that's causing such an overwhelming amount of the harm that using one metric for it, and dare I say TVOCs in that without you spitting at the screen, um, is there a danger we go down that route with particulates, or is there something about the particulates that we're measuring in the home that means it's a different proposition? Um, you see where I'm coming from? That like, whenever you look at a result
Completely.
from the study and you see something I mean, I think PM 2.5 and between 2.5 and 10 represents something like 75% of all the harm in your results. I mean, it's a massive amount of harm compared to everything else. That
Yes,
itself probably deserves scrutiny, I guess.
of course. But there are several ways of looking at this. I think the word that we use is equitoxicity. So we have assumed that all PMs are equally as harmful. But as you mentioned, PM composition varies. So the particulate matter you get from cooking is not going to be the same as the particulate matter you get from a car. There are also, it's also impossible at the moment to separate risk estimates between what you get indoors and what you get outdoors because all the harm is related to measurements outdoors. So we then have to think, well, how much less harmful would indoor PMs have to be in order to be irrelevant? So they'd have to be 12 times, well, not irrelevant, but the same harm as, say, PM10 or formaldehyde from nitrogen dioxide. So they'd have to be 12 times less harmful to be equivalent to formaldehyde or nitrogen dioxide. So the cautionary principle says we probably ought to take these seriously just in case, because what we're finding outdoors is that they matter, and we're still getting a lot outdoors. Um, the other thing is that indoor particulate matter has been evaluated. Um, when you get them indoors, the particulates are fresher. So that means that they have been released much more recently prior to evaluation than they have outdoors. And they've been shown to be coated in polyaromatic hydrocarbons, which are themselves carcinogens.
They,
So
they sound delicious, Ben. Polyaromatic hydrocarbons. What are they?
well, they are themselves uh, uh, a contaminant which have been shown to have clear links to cancer. So, like we said, the particulate matter is not one thing. It is contained of a multiple of different things. The contaminants, the PM that we get outdoors, tend to be trapped onto a filter, and so by the time they're evaluated, any VOCs like PAHs, polyaromatic hydrocarbons, have evaporated off and disappeared. So it's a very difficult thing to quantify. But given how much more harmful than other contaminants PMs are showing themselves to be at the moment, we cannot ignore them.
And I guess one of the beauties of these kind of harm results is it also gives a direction of focus for future work and studies to start learning and say, right, okay, this is causing such a significant amount of harm. This is where we need to direct some research and try and break that apart a little bit and understand it some more. Or my favorite's not on the list. I wonder if there's something we need to study to see if it is more harmful. One of the things I think people forget with indoor air quality is that pollutants keep bad company. So often, by dealing with one, we'll deal with others as well. So we not getting too tied up in knots about whether it's formaldehyde or whether it's NO2. We only have a certain amount of tools in our toolkit to deal with them in a residential
Mm.
setting. And principally, that's exhaust ventilation, local exhaust ventilation, good background ventilation, and source control, where we can identify where that source might be coming from. Not a lot other than perhaps purge ventilation for acute exposure to things that we really can do. As you say, it may start to open up conversations around air cleaning and,
Mm.
filtering and so on. Um, but we have to see things through the context of, okay, now we understand the harm that they're going to cause. What's next? What does that actually mean? What's your hope for this kind of work next of taking the harm caused and turning it into, I don't know, health metrics or something that could be used practically by
Yeah.
practitioners?
Well, clearly, in regulations and guidelines, we'd like to see the six contaminants of concern reflected in them. Um, so that would be the starting point, and various technologies that are designed to mitigate against exposure to them. But I don't think you're going to see a DALI necessarily in your building regulation. I'm sure engineers might not want to, certainly those at the coalface may not want to work with those, and nor should they. So what do they do? Well, we probably need to think about how we include them. And one of the ways that we're thinking about is, you know, you could have threshold limit values, I suppose, but it's a very inflexible way of doing things. Now, if you remember at the beginning, we looked at acceptable air quality, and then we considered DALIs for a number of risks within our society at the moment, and whether they might be, um, well, we didn't make judgments on that, I hope, but that they might be deemed to be acceptable. What if we were to work out a combination of contaminants indoors that might lead to some form of acceptability? And we started to make progress with that. There was a study done in California by Britt Singer and his group who looked at 70 homes, and he found that they all complied with the California Energy Code and therefore with ASHRAE standard 62.2. Now, in those homes, they measured PM 2.5, formaldehyde, and nitrogen dioxide. Now, they didn't measure radon and ozone, but if you take common guideline values for those, and we use our harm equation, our harm intensities, and those concentrations, we find that they give a total harm of 610 DALIs per 10 to the 5 people per year. Now, that's substantially lower than transport. If you go back to our analysis of concentrations in homes that we find in the global north, the total harm from exposure to those contaminants came out at 2,200 disability adjusted life years per 10 to the 5 people per year. Now that's somewhere between alcoholism and smoking. So we clearly want to get it down. Now, the argument could be if we deem that ASHRAE 62.2 is acceptable at the moment, then meeting those standards gives us a harm budget, if you like, of 610 DALIs. Now, we could take that value of 610 DALIs and say you can have any combination of contaminants indoors. If you multiply those concentrations through by the harm intensities so that the total harm, which is done by evaluating the harm from exposure to each contaminant concern together, so long as it doesn't go past 610 DALIs, you're okay.
Yeah, interesting. And
And
I
this
suppose,
is, I was going to just going to add quickly and remind people that this, of course, is the way that WHO already thinks about drinking water. So it's not a novel concept, but it does enable us to objectively perhaps define what is acceptable risk indoors.
and interestingly, with those metrics that you're looking at, PM and formaldehyde and NO2 and radon, for example, if not already, we're very close to being able to measure them at a fairly low cost level on an ongoing basis. So we can also use those metrics over the longer term rather than it just being embedded in code, that they're almost measurable air quality metrics at a reasonably low cost. So it's the kind of thing that we can keep track of in a residential setting potentially over the longer term, which I think could be really interesting. That, you know, we already getting pretty good with particulate measurements at 2.5. That there are low cost formaldehyde sensors starting to appear, or certainly focused VOC sensors on the formaldehyde bandwidth that are getting very good. We know how to measure NO2, for example. Like these key metrics are measurable, which is one of the big challenges. It's fine having a pollutant, but if it's not practical to measure it, not in a lowish cost way, it makes it very difficult to keep track of over the long term.
Yeah, the measuring stuff's hard. It's really,
Yeah.
really difficult. And you have to tell people how to do it too and what with, because otherwise somebody can turn up with their very cheap sensor which doesn't really do what they think it does. They can tuck it in the corner of a room and it won't measure much, and they can say, "Hey, look, I can apply." But that is probably an inappropriate technology and an inappropriate methodology for measuring the concentration of the contaminant you're interested in. So you then have a diagnostics issue. And most standards now, particularly here in Europe, don't tell you how to measure something. They just say it should be this. And that in itself is a problem.
I think that's almost certainly going to be a parallel track of work that's going to have to happen in the larger scale collection of these kind of pollutants of interest effectively. I mean, field measurement is always notoriously difficult and we can get
Mm-hmm.
quite stuck on accuracy, but when you start doing things at scale with big data, you can clean up a lot of that and get a good fingerprint of the performance of spaces over time, and that's really what we're interested in at a chronic level. Um, well, it's really interesting work, uh, Ben. If I could just turn it to you a little bit to start with, how did you even end up in this field of air quality and engineering and the built environment? What was your pathway to being here, and what are you guys doing at Nottingham now, day to day, from a work perspective? What are you currently looking at and working on?